Yeah, good.
Yes, sir.
Sure. Yeah.
So, sir, this is exercise 1B.
One
So
means
on
chapter
this,
1
yes, sir.
or
No, sir,
okay.
this is chapter 1, exercise 1B. I
Okay.
think chapter 2 also, first exercise is called
As
exercise 1.
okay, and this
Yeah.
is the book you said, Paul Halmos, right?
Yes, so finite dimensional vector spaces.
Okay. I have done a bit of this book. Yeah, finite dimensional
Okay.
vector space.
So it was given in the recommended text, so thought of
Yes,
buying those.
this is a wonderful book. Yeah. Let's try the
Yes,
question.
sir.
Yeah.
So using the field axioms, prove that
Okay.
if alpha plus beta
Show that. Yeah.
is equal to alpha plus gamma,
Mm-hmm.
then beta is equal to gamma.
Okay.
So, sir, I was thinking, uh, even now, like, can we just add minus alpha to both sides? Would that preserve the equality? Because that would solve the question.
Okay. What is minus alpha?
So, sir, according, like in the field axioms, minus alpha is defined as the unique scalar such that the scalar alpha, when added to minus alpha, gives zero. That's how they've defined
But
it.
alpha is not a scalar. Okay.
No,
Okay. Yeah.
no,
Sorry.
sir.
It is a scalar. It is. They're calling a field thing. They're calling scalars. Correct.
Yes, yes,
Right.
they're calling the element scalars.
Okay. So yeah, then that's fine. So basically, the definition of alpha you're saying is this.
Yes, unique.
Okay. Yeah.
This is
And
the
unique.
unique.
Okay. So the unique. Yeah. So minus alpha is just a notation we are using, right? For
Yes,
that
yes,
unique
sir.
scalar.
Notation.
So scalar, scalar is just the element of the field. They're calling it scalar because later on
Yes,
they will
yes,
become the scalars of a vector space of a vector.
yes, yes. Even I anticipated that. Yes, sir.
Right. Okay. Now you're saying that can we add minus alpha to both sides,
Yes, sir.
right? So can you use the field axioms to justify that this is equal? Then why is this equal?
Yes, sir. So first we use as addition is associative. So we can switch around the
But why are these
brackets.
two
What
things
we
equal? No, that will come later, right?
Oh,
But why are these two things like?
okay,
Why does
okay.
this imply this? After this, of course, you will say that associative.
That's what, so that is my
That
doubt.
is the
Like I
question,
don't
right?
know if
Right.
yes, sir.
So basically, see, this addition, I think, would be defined as a binary operation.
Yes, sir. Yes.
Addition is a binary operation. So it means that given alpha and beta, there is a binary operation, this, which gives you something which is alpha plus beta, right? So this
Yes, sir.
plus, this plus will be a function from f cross f to f,
Yes. Yes, sir.
right? So it takes two inputs and gives you output which we denote by alpha plus beta. So in that way, you can think of this left hand side as this this plus function being applied to minus alpha and alpha plus beta,
Yes. Yes,
right?
sir.
And also the right hand side is this plus operation applied to this, right? But then plus is a function. Plus is a function, and given to input, given to inputs, it gives a unique output, right? But these two inputs
Yes.
is same as these two inputs, right? So this element is equal to this element in f cross f.
Yes. Okay.
So
Yes, sir.
inputs are same, so output is same. It is just that. Okay,
Right.
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 But obviously, we just say that you can add both sides, which is fine. Okay. Now
Okay.
tell
Yeah. So I
me
was
what to do
looking
after
for like how to
rigorous.
formalize it like this.
Yes.
Yes,
But
sir.
did they? But just to confirm, they mentioned binary operation.
No, sir.
Then
Like
what
they
is
just
addition? What is it?
okay, so they defined uh to every pair alpha and beta of scalars that corresponds to scalar alpha beta called the sum of alpha and beta in such a way that addition is commutative, associative, and then they define zero and they
Okay.
define
Yeah.
minus alpha.
Yeah. So corresponds means that there is a unique, right? So the word
Yes.
corresponds contains a uniqueness, which means that it's a function, right? It's a function from f cross f to
Okay.
f. Corresponds means
Yes,
that
yes.
yeah, to you it there's a unique output, right? Okay.
Yes, sir.
So now what? Now what do you do?
Uh Now we can move around the brackets because of associativity. So
Right.
left hand side we can write it as minus alpha plus alpha
Right.
bracket plus beta. Right hand side minus alpha plus alpha plus gamma. This gives 0 plus beta is equal to 0 plus gamma. Then using the definition of 0, beta is equal to gamma.
Right. Good. Okay. Nice. So this is it.
Yes, sir.
Yeah. You can think maybe if is so in the axioms you can think, is commutativity needed?
Hmm.
You can think about this later. Okay. Is commutativity needed? So mathematically this means that if commutativity is not in the axioms, does it automatically follow from the other axioms?
Uh,
Okay. So basically it would be like
okay.
if you have a set F on which there is that addition operation with all the other rules, then show that it is commutative. Okay, or not. It is needed or not. You can think about two cases in this. First, about the infinite, if F is an infinite set, and second, when F is a finite set,
Yes. So
right?
when it's finite, suppose we can give some counter example or something.
I don't know in which case it is true. That you have to
Okay,
think.
okay,
I mean, okay, I know
okay,
from memory, but you should think first, right? Yeah, which case
okay.
it is
Yes.
true. Yeah, for finite, you can give examples of finite fields first that you can think of. First, you have to think of examples to begin with, right? And then you can see. Okay, I mean
Yes,
these
sir.
are very deep, nice questions. You know that sometimes the commutativity is not given, but it automatically follows. Okay, and the reason could be because it's finite, or the reason could be because the number of elements is a prime number. Okay, so
Oh,
there are a lot of
okay.
different reasons why it can happen, and that's why it's a very nice. Yeah, think about it.
Yes, sir.
Okay, so let's
So
move on.
one second, sir.
Yes.
My mom is calling me. Just
Okay.
one
Yeah.
second.
Yeah. Sure.
Yes, sir. Can you hear me?
Yes. Yeah.
Yes, sir. Now this same exercise, but
Hmm.
exercise 1G,
Okay.
and that says if alpha beta is equal to 0,
If alpha and beta, no, alpha beta.
yes, sir, product,
Hmm.
then either alpha is equal to 0 or beta is equal to 0 or both.
Okay. Nice. So
So I don't know how to start, sir. So I thought maybe using the definition of 0, we can write
okay.
alpha beta minus alpha beta and then uh, do something, but I don't know.
Mm. Yeah, but if the product of two things is zero, then one of them um, has to be zero, right? So did you? So fields are supposed to have inverses, right?
Yes, sir. They've
Field.
defined. Yes, sir.
So what do you know about that inverse thing? Can you state it?
Yes, sir. So they, for every non-zero scalar alpha, there
Huh?
corresponds a unique scalar alpha inverse or 1 over alpha, such that alpha times alpha inverse is equal to 1.
Right. So you have to use this,
Okay. Okay.
right? You have to use this. Try to use this now, maybe, and do it. Yeah. See.
Uh, okay. So, okay. So, sir, suppose alpha is non-zero.
Hmm.
Then what happens is, uh, we can multiply by alpha inverse on both sides.
Yes. Again, by the same explanation that we could add on both
Same.
sides.
Yes.
Okay.
Now, because multiplication is associative and using the definition of inverse, right hand side simplifies to beta.
Yeah.
And on the left hand side, because 0 times any scalar is 0,
Which you can prove.
what happens? Yes, sir.
Okay.
This so beta is equal to 0.
That is it.
Yes, yes,
Right.
yes, sir.
Yeah. So you see, this assumption in fields that everything has an inverse. This is the assumption that makes fields, right? If you remove the
Yes.
inverse assumption, then that is also an interesting structure, right? So if you say, and you should give an example of this maybe now, because it's easy. So field axioms minus inverse assumption, or rather I should say multiplicative inverse
So
for
field
non-zero.
without
Yes. So can you give an example?
sir, in this field should one exist? Like, I mean,
Yes.
one is
I'm only removing
uh,
multiplicative inverse, right? So
okay,
when I
okay.
say I'm removing multiplicative inverse, I'm saying that not every element has a multiplicative inverse. Some elements may have, right? I'm not saying that, but not everybody has.
So I guess so, with 0 included, but it says non-zero. So
Huh?
um,
Because zero cannot have an inverse, right?
yeah.
So apart from zero, there is something else which also doesn't have an inverse, as you said. Yeah.
Okay. So sir, if we take integers, then
Huh?
of course, suppose 3, it doesn't have multiplicative inverse in Z.
Yes,
We have
right.
to go
So
to Q.
exactly. So these are some examples, right? And that is because integers are obviously very important. That is why these things are also studied. They are given a name, and these are called rings.
Rings. Okay.
And they are very important. Yeah.
Yes, sir.
So yeah, this is okay. All right. So let's move on. And also another thing is that this condition itself is so nice. Okay. This condition itself is so nice that all rings which satisfy this condition are given a name. Okay, let's
Oh,
talk about that
okay.
a little bit, because in the example you gave, it connects with that. So let me put it properly so that there's not confusion. Let's say that R is a set, okay, and there is plus and multiplication, two binary operations. And I can just say it's field without multiplication, but it's better to write it properly. Two binary operations. And so I said with two binary operations, associative, okay. Let me not put commutative, not needed, okay. Associative, uh, this is it, okay. And obviously distributive, okay, distribute over each other. So I'm just writing that as distributive, okay. So like whatever you have read, so there is a plus b, a is an, so given a and b, there corresponds an element a plus b, so which is, so on. But also it is associative, so it is like this, okay, and so on, right? There is multiplication like this, and there is distributivity, so I'm not writing that.
So, and what about additive inverse?
Right, so let me put additive, let's put additive inverse, but let me not put unit, no need. Okay, right,
Okay.
yeah, so I'm putting additive inverse. Okay. Even this can be said in other way, like it's a group plus another operation, but no need now. So additive inverse we are putting, and I'm not saying that there is a unit, you can add it, yeah, but I'm certainly not putting multiplicative inverse. Okay, it may have multiplicative inverse, it may not have multiplicative inverse. It's not a requirement. Okay, it's not a requirement. Okay, so this structure is called a ring with all these information, with a set and this two functions, binary operations. It's called a ring. And plus, if the star is satisfied, okay, so a ring with this property star, okay, these are very important structures, ring plus star, okay, these are called domains. Okay, these are called domains, just a name. Okay, so we are slightly moving closer towards field, right? That even though you do not have inverse, so you may not, so from here you may not have inverse, but you can still sort of cancel one of them. Okay, it's something like that, right?
Okay.
Yeah,
Yes, sir.
can you give an example of this?
Uh, so isn't every field a domain?
Yeah, every field is a domain, certainly, that is true, but an example where it's not a field but it's still a domain.
Okay, it's not a field, but it's still a domain. So, we have, okay, so I guess we can use positive integers only. But
uh,
no, sorry, sir.
Integers, need to use
All
all of it.
integers. Yes,
Yeah,
yes.
positive
All
integers are
integers.
also a structure, they are also called something, but
Yes.
then you won't have additive inverse.
Yeah, no editor. So we won't have zero there.
Exactly. And so we have this. Now can you give a non-example,
Um,
so where two non-zero things multiply to become zero?
Also matrices.
Yes, certainly. Right, matrices you can take, yeah. So these are the things you have learned. Matrices, you can even take like integers modulo some non-prime, z mod 10
Yes,
z,
yes,
whatever is the
yes, sir.
notation, maybe not this, but yeah. So this is the things. So these are domains and non-domains. These are very important aspects. So a lot of things that we prove, problems we solve, they happen for these reasons, that something is a domain and then something happens. Okay, you will see those things in more detail. What you can prove, maybe this you can also try for homework. is that this plus this. So you remember, I've not even put commutativity. You can put commutativity and prove it, but I'm not putting that condition. So it's, in a way, it's a more harder question. It's a harder question, but you can put commutativity. Whether it's harder or not, that you see. Yeah. So ring plus this plus finite. This actually implies it's a field.
Okay.
Okay, like
So,
automatically.
hmm, like I don't know how to approach it, sir, but I'll try.
Yeah, think about it. Yeah, basically inverses start existing. Okay, like,
Okay,
yeah,
okay,
you
okay.
have cancellation, but
Oh,
if you
because it
put
has to loop back.
it, kind of, yes, that's the reason. That's the kind of the cyclicity, and that when you iterate, then you actually get the inverse, something like that. But you have to prove it. These are
Yes,
actually
yes.
combinatorial questions. There is no hype. There's not any algebra. It's just combinatorial things. Like for example, you see, you look at ZP, where you have integers modulo prime. You see that everything has an inverse, right? It is a
Yes,
domain,
yes.
yeah, product of two coprime elements remain coprime and so on, and it starts having an inverse, and the inverse actually comes through that looping thing only, right? Because a to the power Fermat's theorem gives you identity, right? So if a to the power p
Yes, sir.
minus 1
Yeah,
gives you
yeah.
1, it means that for the inverse of a is a to the p minus 2. So the inverse actually comes through that cyclic process. But in your proof, how you will do it, that is up to you. So you see, it's a prototypical example is ZP. Okay, but yeah, think about it. These are very straightforward questions.
Yes, sir.
Okay,
Yes, sir.
so let's move forward. When you do more, you will see that these are very important things. Yeah, and one can easily do small like problems in this, which are sort of unsolved, but like nobody sort of focuses on them. But in the beginning stages, you can work on those small questions. But first, you get comfortable with these structures more, then we can think of those.
Yes, sir.
Yeah. Okay, so
So,
let's
sir, I was doing analysis as well, Bartle and Sherbert.
okay.
Like I wasn't doing it, I just glanced through it. I was seeing like what to expect, and I saw one exercise, sir, which I feel like I got the correct proof. So, can you like check my proofs?
Yes. So sure. Just 1 second.
Yes, sir.